So anyway,
I've never heard of a professor doing that.
Yeah, he was like, "Yeah, I watched your group, Lauren. So good job." It's like, "Thanks." Okay, so we will start with Sarah's questions, I guess. And did one of you do Sarah's?
I didn't.
I did number 2.
Okay.
And I have number 1.
I think Mason must have written it maybe in Google Docs. I'm not sure.
I mean, I feel like number 1 was pretty easy because it's like, I don't know. Because, like, I don't know. Never mind.
I felt like the first one was easier.
Yeah. I didn't get C, but.
Yeah. Me either.
I'm gonna be honest. This week's been kind of crazy because I was in a car crash a couple weeks ago, and so I've been going to the doctors.
Oh, no, I'm sorry.
No.
And the doctors in Utah and living in Idaho, I had a lot of time to do stuff.
Oh no.
Oh no, that's terrible.
I promise next week it'll be better.
No, yeah, you're fine. And I was telling Landon, I got home late from work today, and it's just a crazy week. I'm with you. Okay. Well, looking at 1 and 2, I mean A and B on part 1 or on question 1, they both look right. Do you guys agree with those being right?
Oh, I haven't even looked. Let me check.
Oh, on the Google Docs.
Okay, yeah. Never mind. Yeah, I've seen those. Yes, that's what I got.
Right, and that's what I have also. We can go back and do part C if we want once we like agree on the rest of them, I guess. Unless you just know how to do them now. Because I don't. I didn't get that one either.
Linear velocity. Like, I know how to do angular velocity. I'm trying to think. Would we just use a kinematic equation? No. Yeah, see, I don't know. So.
Given that the Earth is raised
Okay. So we have
at the Earth's surface, yeah. So
it's basically how fast it's rotating, right? It doesn't matter, like. Oh.
Right from.
So we basically just need to know, like. Well, we would need the circumference of the Earth, right?
Which we could find.
Yeah, and then we have how long the period of rotation, and then we would just use those numbers to solve for the velocity.
So the circumference divided by the period.
Yeah,
which
distance
is
over time.
Distance over time. But we're not going to use angular, so I'm going to put it in here. This meeting may be a little bit longer, guys, but we can work through this. Okay, so I'm putting it into Google Docs. Velocity equals distance over time. And then, okay. So we have 2.
So then 2 pi r. So 2 pi times
6. I'm sorry, 6.4
times 10 to the 6 meters.
So I got 40,212,385.
I'll grab my calculator.
Yeah. So you got okay, yeah, I got that as well.
40.
So that's the total distance that it needs to travel.
Right.
And then divide that by
86,000 seconds divided by 86,400. Or that 86, 16, 4.095 seconds. I was about to hit enter, assuming it would do the math for me, and it won't. Okay. $466.95 meters per second. Okay. Did you put that 2 in there, Landon?
Yeah, I'm just doing 2. It took me forever to find the pi symbol.
I get it. Okay. Oh, what the heck? That's not right.
He used different font, and I can't fix it. So, can you highlight stuff in this document? Because I can't.
Yeah.
Oh, there we go. Oh, I got it. It's taking a long time. Yeah, it's like he has a different font or something.
For which one?
So weird.
Oh, because they did it. They added a formula.
Oh, okay. I was gonna
That
say,
formula is in a different font.
I did not know you could do that in a Google Doc.
Yeah.
It's pretty nice.
And I'm like trying to highlight it, and I was like, what the heck?
It's nice because you can make it look like the real formula without trying to have to figure out what it says.
Oh, okay.
But it's harder because it takes a lot longer to type it in.
Interesting. Okay, well, I got the same thing for C, so.
Okay, cool. Then let's go with that because that makes sense. We're just talking linear velocity.
Yeah. Okay, so 2. I did 2.
Okay.
It wasn't too bad. This one wasn't too bad either. It's basically the same question, but you're using angular velocity. So rotating space station is said to create artificial gravity, a loosely defined term used for an acceleration that would be crudely similar to gravity. The outer wall of the rotating space station would become a floor for the astronauts, and centripetal acceleration supplied by the floor would allow astronauts to exercise and maintain muscle and bone strength more naturally than in non-rotating space environments. If the space station is 200 meters in diameter, what angular velocity would produce an artificial gravity of 9.8 meters per second squared at the rim? So then I put a picture of my work. So the equation I used was the acceleration equals W, which is angular velocity, W squared R. And so then I just solved it, or set the equation equal to W, and then just plugged in the numbers and solved. And then I didn't know if he wanted it in revolutions per second or per minute, so I just put both in there.
Okay. Yeah, yesterday I asked him what units for something. I asked him what units for period he wanted, and he said always seconds.
Okay.
So I would assume he wants revolutions per second there, but
yeah, I'll just delete this minutes then, because
okay.
it's in minutes on my work as well if it's really a big deal. But
yeah, it's there. Yeah, I think it's probably good to have it in seconds. Okay.
Yeah.
I don't want to delete your work, but I don't like all the blank space. Okay.
I don't blame you.
All right. 3 and 4. Was that you, Ashley, or was that Mason?
That was me.
Okay. Talk about yours.
So define I'm going to say this wrong. Centripetal force. Can any type of force, for example, tension, gravitational force, friction, and so on, be a centripetal force? Can a combination of forces be a centripetal force? So a centripetal force is any net force causing uniform circular motion. This force does apply to tension, gravitational force, and friction. Examples of that would be like the tension in a tetherball pool, the force of gravity on the Earth that affects the moon, and the friction caused by rollerblades when skating. A combination of forces can still create a centripetal force. An example of that would be a tube of spinning, the tube on a spinning centrifuge.
Yeah,
That's good.
Yeah, that sounds perfect. I couldn't have said it better.
So next one. This is the one I wasn't so sure about.
Okay.
The way it was asked. What is the direction of the force exerted by the car on the passenger as the car goes over the top of the amusement ride picture in figure 6.33? Under the following circumstances, the car goes over the top at such a speed that the gravitational force is the only force acting. The force goes over the top faster than the speed. The car goes over the top slower than the speed. So for A, what I got was if the car can go at just the right acceleration, the gravitational force will create enough centripetal acceleration to allow the car and all the passengers to make it safely through the loop. The direction of the force would be in a forward and downward position. Does that sound like what it was asking?
Because
that's what I got.
What's the direction of the force? Downward and.
Because I didn't know how to explain that. Because like the way the book was explaining it was basically like that is like having that situation would be like the perfect loop basically. So you just have a continual motion.
Right.
So I don't know how to describe that a force.
Yeah, that is. I don't know. That wording's interesting.
Yeah. Such a speed that the gravitational force is the only force acting.
I
Hmm.
It's basically the perfect loop.
Mm-hmm. That there's
Yeah,
no
not-
friction or anything.
No, just the force of the art. Which I actually learned a lot about amusement rides during this lesson.
Force exerted by the car on path.
That's fine.
This is a very weirdly worded question.
I read that and I was like, I don't know how to go about this.
Well, the thing that's confusing me is like, in what situation would there only be gravitational force? Because it's like, if the car is moving forward, it'd be pushing the rider forward.
Mm-hmm.
I don't get that. That is strange.
We could ask him about it. Like, I mean, we could just submit this as is, but then ask him, like, and he always explains. He does a really good job of explaining.
Mhm.
And so, well, he explains in detail most of the time.
Yeah.
And so we could always just put in the comments before we, like, when I submit the document, I can put in the comments, like, hey, we didn't understand this question. Because I'm just trying to think, like, I mean, I think what you explained makes sense, but I'm not sure if that's what he wanted. You know what I mean?
Yeah. Though, the way the book was explaining it, that because if you can't have a acceleration and force of gravity that equal the centripetal acceleration, it will actually cause the cart not to be able to make the loop.
Oh, yeah, that makes sense.
Backward force. So like a negative force. Again, I
Mhm.
don't know how to explain the force on that one.
Backwards motion. I think that sounds good.
Yeah, that sounds good to me.
And so then you're saying if it were faster than the normal speed, that, like, instead of just going forward and off of the loop, it would just continue to go kind of back vertically again?
Um,
Or what were you trying to explain with B? Sorry.
so basically, it's almost the same principle as A,
Mm-hmm.
but it creates a tighter curve, which basically means you're going to do the loop faster and in a faster motion, a faster force, basically.
Mm-hmm.
So yeah, that's what the book was explaining. That's how I read it. I might have read it wrong.
Yeah.
But basically, it's kind of almost just like A. You're just doing it at a faster centripetal force, basically.
Okay. Yeah, I don't know. I think we should leave it because I don't think that you're wrong. I don't know how you feel about that, Landon, but I don't feel like you're wrong, Ashlee. Maybe, I mean, we may be missing part of what he's looking for, but we can ask him.
Yeah, I wouldn't know how to change them. I think they sound good to me. So yeah, we can ask to see what he says, but
Okay. Yeah, maybe ask him to kind of explain that one a little bit to us. And actually, if we post on that discussion board post too for the group work, I think he answers on there, and he reads that, and that way we can all kind of see his feedback, and hopefully he'll answer before he grades.
Do you want me to hurry and post it on there right now?
Yeah, if you want to do that. Because he may even get to it before we get off. He's typically online, I've noticed. So,
This is question 4, not 6.
yeah, 4. It says he's online right now, so we'll see. Maybe he'll answer.
I say we are confused on
Question 4. Which questions did Mason have?
I had 8. And
Oh,
which
that's
ones-
right. You had just 8, so he
So you
had
must
5
have-
and 6.
Okay,
They
I'm
already
doing
had
5
common?
right now.
That was so. Wait.
Okay.
Okay, I posted it.
Awesome. Cool. I have a feeling he'll respond quickly.
Okay. So I just punched in the equation that Mason had for 5.
Mm-hmm.
I got the same answer, 18.9 meters per second.
Okay, and I looked at that formula, that equation,
Mhm.
and that's what I would have used.
Yeah.
Looks pretty
So-
cutthroat.
Mm-hmm.
Works for me.
Yeah.
Good.
Pretty
Thinks
straightforward.
that they're not here to explain them, but that's okay. That's all right. And the thing is, I was almost like, I'm not going to be able to make it to the meeting, but good thing I made it back.
Mhm.
Okay. And for 6, we can read through 6. Part of riding a bicycle involves leaning at the correct angle when making a turn, as seen in figure 6.36. To be stable, the force exerted on the ground must be a line going through the center of gravity. The force on a bicycle wheel can be resolved into 2 perpendicular components. Friction parallel to the road, this must supply the centripetal force, and the vertical normal force, which must be equal to the system's weight. What's the question? Oh, A. Show that theta is related to the speed v and radius of curvature r of the turn in the same way as for an ideally banked roadway, that is theta equals tangent, inverse tangent, velocity 2 over, I don't know what that formula is supposed to say. Velocity squared over rg. Yeah, that's what it is.
Yeah.
So Mason said the rules for a frictionless banked curve allow us to find out horizontal and vertical components, saying n times sine theta equals m equals v squared over r, which is our horizontal component of centripetal force. We can also say the vertical forces are equivalent to normal force and the weight. So n times cosine theta equals mg. With these 2 equations, we can solve for n and set them equal to each other, which can be reduced and simplified to tangent theta equals v squared over rg, which is the same as theta equals inverse tangent times velocity squared over rg. So he just derived that formula from combining the 2. Looks good to me. Do you guys have any questions about that?
Well, that looks perfect.
Yeah, it looks good.
I agree. Okay. Calculate theta for a 12 meter per second turn of radius 30 degrees as in a race. Okay.
I just plugged this one in and I got the same answer.
the same
So he
answer.
at least plugged it in right.
Yeah, as long as that formula is right. Inverse theta, 12 squared divided by 30 times 9.8. Yeah, that looks good to me. It looks like the right answer.
Okay.
And that is it for that question, right? That's A and B.
Yep, A and B.
Perfect. Okay. Number 7 was mine. And I didn't give too much detail because I didn't want to I wanted to make sure I was sure. But it says that 2 friends are having a conversation. Anna says the satellite in orbit is in free fall because the satellite keeps falling towards Earth. Tom says the satellite in orbit is not in free fall because the acceleration due to gravity is not 9.8 meters per second squared. Who do you agree with and why? So first of all, I thought about the fact that free fall doesn't necessarily mean that acceleration due to gravity has to be 9.8. It just means that it's falling without any other forces like preventing it from falling. So it just falls with the force of gravity, but it doesn't mean that gravity has to be that. And so I said that I agree with Anna because the satellite is following the curve of the Earth, the curvature of the Earth. And so it's continually falling towards the Earth, but it's also falling against the curve. So it's always falling, but never actually entering Earth's atmosphere because it just keeps going around. So I said it was a free fall. There was, I was trying to read about it in the book and get more information. Do you guys have any additional thoughts about that so I can kind of collect my thoughts?
I mean, I would agree. I don't think that. I mean, you can still be affected by Earth's gravity, even if it's not the full 9.8 meters per second squared. I don't think that's. But I do agree that it is in constant falling motion. It's falling, but it's also. I don't know. I feel like it's so hard to describe some of these concepts.
Yeah. Oh, yeah, definitely. Without making them sound like.
Yeah.
I don't know. I feel like we make them sound too two-dimensional when we talk about them. It's very hard to explain it kind of three-dimensional.
Yeah.
You know, like what's going on.
Yeah.
But anyway, sorry. What were you saying?
I agree with you. I don't know how else to say it.
I didn't know if you had another thought. I'm gonna say also regardless of the acceleration due to gravity. You can still have free fall motion. Except, just added a little bit to that answer.
That sounds good.
All right, number 8.
Alrighty, so mine was number 8. So calculate the magnitude of the acceleration due to gravity on the surface of the Earth due to the moon. I feel like the wording was so weird on these.
I know. And I'm sure it has to do with it, the fact that it's an online class and it's really hard to kind of communicate, but
yeah.
But still.
So yeah, so if you look down at my picture down below, I use the equation AM, the acceleration, equals g mass over radius squared. So for the g, it's that constant we used in lab, and then m is the mass. So for A, we're talking about the moon, so it's the mass of the moon, which is 7.35 times 10 to the 22 kilogram. And then the radius is the distance between the Earth and the moon. And so then you just plug all those numbers in, and it gives you 3.33 times 10 to the negative 5 meters per second squared. And that's the influence the moon has on on the force of acceleration of Earth's gravity.
Okay. That's good.
Yeah, thanks. And then for B, it's the same. Everything's the exact same except for some of your values for M and R. You switch it out for the mass of the sun instead of the moon and the distance between Earth and the sun, which gives you 5.93 times 10 to the negative 3. So then C goes on to ask, find the ratio between the influence of the moon versus the sun, and then talk about why the moon why the tides are related to the moon. So the ratio I just found by dividing the sun over the moon influence, and it came out to the sun is 178 times more influential on the gravity than the moon, which I was pretty surprised by. So that got me thinking why the moon is what has the influence over the tides. And so the sun is so far away from Earth that although it has the stronger magnetic force, the Earth kind of feels it as a whole all over the Earth. It's not just one part of the Earth that feels that force more than the other, just because the distance between one part of the Earth and the other is so insignificant compared to how far the sun away is. whereas the moon is a lot closer to the Earth, and so the force of acceleration on the gravity of Earth is felt more strongly on certain parts of the Earth, which is what makes the tides shift. Does that make sense?
Mm-hmm.
So yeah, that's what I put.
Nice. Yeah, that sounds good. I
right.
don't have any questions about that.
Okay.
Looks good to me.
Makes sense to you, Ashlee?
Yeah.
Okay, so who had
Okay.
9?
I had 9. So I just have to finish this calculation really quick. But basically, here's what I did. So I used the Kepler's formula because we're looking for the mass of Jupiter based on the orbits of the moons. And so Kepler's formula basically helps us to find the mass of the parent planet, in this case Jupiter, based on the satellite or the smaller mass, the object that's orbiting it. And so there's a formula, Kepler's formula gives this formula r cubed divided by period squared equals gm divided by 4 pi squared. Sorry, I lost my train of thought. And so then I basically rearranged that formula to solve for m so that we could solve for the mass. And so then if you can see on Google Docs below, the original formula is the derived formula to solve for mass. And then I just picked one of the moons. So I picked Europa, and it gives you R and it gives you T. And so I put those in, and I multiply by 4 pi squared, and then you divide by the gravitational constant. And does that look right so far? I'm just trying to get an answer.
Yeah.
But does that look okay?
Yeah.
Yeah.
Okay. And then, so the gravitational constant is 6.67 times 10 to the negative 11. Now this divided by, 6.67. Okay. So,
I do have one quick question. For R, you put 6.71 E8 to the...
Oh, yeah. So here it gives kilometers.
It's cubed. Okay, I'm sorry.
Yeah, so it's cubed also, but I've changed it to e to the 8 because it's e to the 5th in kilometers, and so to get it into meters, I did e to the 8th because I just moved it 3 places.
Okay, that makes sense.
Does that make sense? And then I cubed it.
Okay.
And then I took days and converted it into seconds. And so then I divided those and then multiplied it by the 4 pi squared. And divided it by the gravitational constant. And this is what I got. I should put commas. 4,143,162,267.32 kilograms.
Jeez.
Yeah. So, or I guess you could also say like 4.14 e to the 2, 3, 4, 5, 6, 7, 8, 9, 10 kilograms. And that's what I got. Now, the actual mass of Jupiter is 1.8. Oh, that's not what I got. It says that the actual mass of Jupiter is 1.89 times 10 to the 27th.
Okay, 1 second. I'm looking at my equations and I'm comparing with yours. So you have r cubed over t squared equals gm over 4 pi squared, yes. So then you derive the m equals 4 pi squared r cubed. Okay, I see what happened.
Okay.
So in your second equation, the m equals the r cubed.
Mm-hmm.
So see how you have r cubed over t squared?
Yep.
That t squared just needs to be down with the g.
Right. Yep. I see that.
And then that should fix it.
So, because that's going to multiply, it's going to go to the top. And then this t squared, oops.
Yeah, that'll be r
This
cubed.
t squared is going to go on the bottom.
Yeah. Awesome. Okay, so now
That
let's
makes so much more sense. Okay, so now I'm going to change this in here. Divided by
oh my goodness, that's what I did wrong.
sorry.
No, it's okay. I'm trying to figure it out as well.
Now, do I multiply? I square pi first and then multiply by 4, right? Or would there be parentheses around that and it'd be 4 pi and then square it?
It's a good question. I'm trying to figure that out. I'm pretty sure it's just the pi squared.
That's okay. That's what I would.
Pi squared. And so you want it in seconds. We're putting it in seconds, right?
Mm-hmm. Now I just put in.
Okay, I got a different number for seconds.
Okay, yeah. So that's what I was gonna say is I just put in the 24 hours one. I didn't use the actual one, which I guess is gonna probably make a pretty big difference.
3.55 times 24 times 60 times 60. So I got 306,720.
Okay, hang on. You got 30 what? 305? No.
306,720.
Okay, yeah, that's not what I got either.
Okay, so what are you doing to find your seconds?
So I took the 86,164.095 seconds.
Oh.
But I don't know, do we have to consider the fact that a day is different on Jupiter?
Oh my goodness, I don't even know.
Because the period
just-
gives it in days, but is it in, like, I don't know. Is it in Earth days? If that makes sense.
Yeah, I don't know.
I would assume so.
Well, hey, let's see. Okay, well, yeah, sorry. So let's try that time. Let's see if that fixes it.
I put it in there in the bottom.
Okay.
T equals 3.55 times 86,164.
My goodness. I keep getting the wrong. Let's see.
But are you multiplying those? Like, what are you doing?
Well, because I got 5.8 times 10 to the 32.
Seconds?
No, sorry, for the final answer.
Oh, for the answer. Okay.
Which is a
now,
bit
it's not
too
going to
big.
be exact. So, oh, you know what? Oh, okay. So I was wondering why it was giving us a mass there for each moon, and I thought that was the mass of the moon. That's the mass of Jupiter. I was wondering why they were so close in size. I think that's the mass in Jupiter according to that calculation, what it should be.
Yeah. Okay, yeah.
Like when it says compare your results to with the actual mass,
Mm-hmm.
I think that's what it's looking for. So that should be the answer that we're getting, or at least somewhere close to
Okay,
that.
so here's something we could try. The length of a day on Jupiter is 9 hours and 56 minutes. So maybe let's try that for time and see if that gives us anything.
Okay, so 9 hours.
60 times 60 equals plus.
9 times 3,600 plus 56 minutes.
So I got 35,760 seconds.
Plus. How many did you get?
35,760 seconds.
Okay, per day.
Mm-hmm.
Okay, times 3.55 days. So I got 126,948.
For time?
For seconds total.
Oh, sorry, say that one more time.
126,948. So I multiplied that by 3.55.
Oh my goodness, yes, sorry. That's you're right, yeah. Yes, okay.
Okay. So then
I'm still getting the wrong answer. What on earth?
well, maybe we don't have, maybe I don't have the formula set up right or something. But are we getting an answer close?
Well, I just got 1.4 times 10 to the 33.
Yeah, that's way too big. Okay, let me work through it. Let me put in my calculator one more time. See if I can get it. See if I get to the 33 too.
Does have to be 8. Oh my goodness. Have you been squaring the time?
No.
Oh my gosh, I haven't squared the time once.
Oh my gosh. Okay.
Holy cow.
But I didn't do it when we did Earth days either. So
Me either.
okay, so I'll do Earth days if you want to do Jupiter days.
Okay, let's do it.
Okay.
Oh my Lanta, how did I forget that? Okay.
Oh shoot, and I didn't cube the R. Hang on.
Okay. Well, so using the Jupiter days got pretty close. 1.11 times 10 to the 28.
Yeah, that is pretty good actually. Give me 1 sec. Sorry, it's taking me a lot longer because I don't have my scientific calculator.
No, you're good. I could honestly do it really fast because all I have to do is change the
Oh
seconds.
yeah, that's fine. Do that.
Oh. Whoa. Okay, yeah, so I'm guessing it's not Earth days.
Is that too much? Okay, then let's just go with that. Let's just assume it's Jupiter days. Okay. So I'm going to change all this in here. Space on one day on Jupiter equals 9 hours and 56 minutes. Equals 35,760 seconds. T. Oh, you're changing it.
No, you're good. What the heck?
I guess I should put this here. So that's wrong. So what did you say you got for the mass?
1.11 times 10 to the 28. Which honestly isn't super close, but I mean close enough.
Yeah, it's not. It's
like
not
an order of
terribly off.
Yeah.
So, all right. I think that looks good. Thanks for helping me work through that one.
Yeah. There we go. Okay, so then that's 9.
Okay, and that's all of them. Should we see if he answered our question? I don't think he did. Nope.
Oh, just he didn't?
Mm-mm.
Okay.
We can just leave it as it is, I guess. And
Yeah.
I can wait until later tonight to submit it, and if he explains it, then we can go in and change it.
Sounds good to me.
So if either of you are on the discussion board and see that he changed it, or that he answered the question, and you have a better understanding and you want to change it, then go for it. And I just won't convert it to a PDF until like 10, and then I'll submit it before 11. So that way, if you want to add or take away anything, go for it, and then I'll just do that at like 10.
Sounds like a plan.
Okay, so then the next thing we have to do real quick is divvy up next week's.
Yes. And then we need to send out an email to Mason as well.
Right. We can do that.
pulling it up really quick.
Nope, you're fine. There are 9 questions next week.
Okay.
One
There's 4 of us.
is, there's 4 of us. The first one's conceptual. The second one has a lot of parts. Third one's is conceptual. Fourth one has a couple of parts. 5 and 6 are long. 7 is conceptual, and 8 and 9 are long. So we're gonna have to take 2 each, and then someone's gonna have to take 3. So 1, 2, and 3 has 2 conceptuals and 1 question. I can take 1, 2, and 3.
Okay.
And then 4 and 5 are both problems. I don't know, we could give
I
those to
can do
Mason
those.
if you guys want. Or if you want to do those, Ashley? Okay.
Sure.
So that's 4 and 5. 6 and 7. So 7 is a conceptual. It says list the 4 different forms or types of energy and give an example of a conversion for each of these. Okay, so that's a conceptual. And then 6 has 3 parts to it.
So maybe what we can do. Oh yeah.
And
6 is
then
kind of big.
Yeah, 6 is kind of big. And then 7 has 1. I'm sorry, 8 has 1 part, and 9 has 1 part.
Okay, so 6 and 7 could be go together.
Go together, and then 8 and 9.
Mm-hmm.
So you get to pick which ones you want.
I'll take 8 and 9. I feel bad. I feel like I'll take 8 and 9.
Okay. And then we'll give Mason 6 and 7.
Okay, sounds good.
Okay, and then we'll still try to work through all of them so we can help each other out. And I'll tell Mason to create a Google Doc for week 6 too.
Awesome. And I feel bad if you or Mason want to break with like the submitting and starting the meet and the document and everything, I can help out if you ever need.
Okay. Yeah, I mean, I don't mind. For my other class, we have to do Google Hangouts too. And so I just knew how to do it. And I was like, well, if no one else knows how to do it, like I just didn't know. So I was like, I could do it. It's totally not a problem because it means that I'm here. But if I'm ever not going to be here, I'll just let you know and you can start it.
Okay.
But for right now, it's really easy for me to just open it up. And this way they're all in one place too. They're all on my page if we want to go back and look at them or need to resend them or something. So.
All right, sounds good.
And then Mason may want a break. So you could always ask him if he does.
Okay, I'll ask him.
Yeah. All right. I'm going to